Okay, friends, we are now starting chapter 4, where we're talking about congruency and isosceles triangles, a lot with congruent triangles. We'll be doing some proofs and things that we're going to work with. I am very excited. This is one of my favorite sections to teach because it kind of makes sense with things that we've learned in the past. But today we're going to try to prove triangles congruent, and we're going to talk about different figures being congruent also. So the first thing we need to remember, what does congruency mean? When I asked you like for congruent angles, you knew those are angles of the same measure. If I talked about congruent segments, that's segments of the same measure. We always had the same size and the same shape. So we know geometric figures are congruent if they are the same size and same shape. And we know that's going to be the case. So same size, same shape. That's why we talked about congruency. Now we're talking about some other terms. Now we talked about corresponding angles before, and when we talked about parallel lines, corresponding angles have been like angles 1 and 2 here. Now corresponding angles, remember, corresponding means going with. It matches up with something. So we're also going to use the term corresponding angles when it comes to triangles. We'll also talk about corresponding sides, sides that go with. And so what are corresponding angles and sides in relation to congruency and similarity? Well, corresponding angles and corresponding sides are in the same position in polygons with an equal number of sides. So that means they correspond. Like if I have a side that matches or corresponds, they're going to have similar traits. Or if I have angles, they look the same. They're in the similar locations. So we have to be very careful with that. An example of that would be like two triangles here. Notice I'm going to make two right triangles. The two boxes, the right angles, are the ones that correspond. The two sides that are the same length, those are the ones that correspond. They're in the same position. They're the same location with them. It's basically a matchy-matchy game. So here's the definition of congruent polygons as a result. It says two polygons are congruent polygons if and only if their corresponding sides, which means the matching sides, and corresponding angles are congruent. All right, so here's the key. They're going to be congruent. So if and only if their corresponding sides and corresponding angles are congruent. Thus triangles that are congruent are the same size and shape. So triangles that are the same size and shape are considered congruent. They have this one-to-one correspondence. So here's an example of this. And I think we'll do a little bit easier if we write these. We have triangle ABC and triangle DEF. We're going to let A be blue. We're going to let D be blue because those are the ones that are the same. They're corresponding. They match. We'll let B be red, and we'll let E be red. They're the ones that match. They correspond. And then we'll let C, and we'll let F, and that's supposed to be a C, but it's really badly drawn, so we're going to do it like this. These two correspond because they're the ones that are the same size. Notice they match up. There's a one-to-one correspondence. They're matchy-matchy. They have to be named the same. But that also means their segments that are between those are going to have to match. We know that AB and DE have to correspond. We know that BC and EF have to correspond. We know that the angles with the same, between the two angles that are the same, the corresponding sides have to be same. In order to name congruency, everything that's the same has to match up. I even name my line segments so the vertices match up. So here's what we say here. Triangle ABC is congruent to triangle DEF. A and D have to match because they're in the same position. B and E have to match because they're in the same position. C and F have to match because they're in the same position. In fact, let me put these in the same colors here that we were doing earlier. Here's B, here's E. Now, notice everything matchy-matchy. If I name segments, I know segment AB has to match a segment DE. Notice how they're matched over here. I know segment BC has to be, and I'm going to rewrite those in so you can see them a little bit better, has to match EF because BC and EF are in the same locations. Those have to correspond. They have to match. C and F have to correspond. Now the same idea happens for any polygon. If I tell you these polygons are congruent, their congruency is written in such a way that you can play matchy-matchy. That means I know angle P and angle W are congruent. I know QR and XY are the same thing. I know segment RS, notice right here, corresponds with YZ. I match it perfectly from my congruency. Now we also need to remember two vertices that are endpoints of the same side are called consecutive vertices. So for example, remember P and Q are consecutive. They're one right after each other. Even P and S are consecutive. We play the matching game. So let's get our first theorem down here. All right, and this is actually kind of common sense with this, and then we're going to go through and work with these. Okay? On our theorem, it says the following. If two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. Now, actually, I want you to think about this one. It's really kind of a common sense type approach. Let me give you an example of what I'm talking about here. Here we have two triangles, and they don't have to be the same size, but their angles are going to have to be the same size. So here we have A, B, C, and then we have D, E, and F. And here's what they're saying, okay? If A and D are congruent, all right? If angle A is congruent to angle D, and if angle B is congruent to angle E, then you can assume angle C is congruent to angle F. Now, why is that the case? Well, basically, it's from the triangle angle sum theorem. Remember that says if the angles of a triangle add up to 180 degrees, all right? So if these two angles are the same size with these two, what do we know about our third ones? They have to be exactly the same as a result. All right, well, we're going to do examples in just a moment now.